Hey guys, let's continue our discussion on soils and soil formation. So, so far we've been talking about soil formation as a function of both physical and biological processes. So the physical components, remember, included both weathering, the chemical and physical breakdown of rocks, and erosion, which is the transport of that material. So that adds to the abiotic components of soil, so the material that comes from rocks, things that were not living. But of course, there are also organic additions, and these are essential for the productivity of soils. Anything that dies in a forest, for example, falls to the forest floor, whether it's the annual leaf loss of deciduous trees or a tree falling over or an animal dying. The moment that happens in a pretty slow process, at least here in a temperate ecosystem, is the process of decomposition, right? So this oftentimes begins with detritivores, right? So if a tree trunk falls, for example, we can see there's all these macroinvertebrates. The horned beetle, for example, bark beetles, carpenter ants. What these guys do is they mechanically break down the organic material. That increases the surface area and therefore allows the decomposers to then chemically break it down. So fungus, for example, and bacteria will convert the organic log, this organic material, and convert it to inorganic nutrients. Right? That's important. So nitrates and phosphates and other things that are required for the productivity of plants. Now, this process is really important for soil formation and development. And the reason we're concerned about organic additions is because, well, first of all, as we described, the addition of nutrients, which are critical for the cellular processes of plants. And then, of course, that material is passed up through the food web. But organic additions also improve the soil structure, right? The partially decomposed and fully decomposed material actually improves the soil structure by making it light and fluffy. This dark, nutrient rich humus improves the structure. It almost behaves like a sponge, so when it does rain, it's really good at mopping up and absorbing that excess precipitation, which can ultimately prevent flooding, but it also allows for the water to infiltrate into the soil so plants can use it. And it also is going to help retain those nutrients as well, instead of it just leaching out like it would in a sandy substrate. It turns out that organic additions also moderate the temperature, right? So an organic covering of leaf litter, for example, is going to cool the soil in the summertime, and it'll allow the temperature to be somewhat warmer in the cold, harsh winter months. So a moderation of temperatures is critical. Finally, this covering, and perhaps most importantly, is really important for protecting the topsoil, right? So if we're talking about harsh Arctic winds or runoff and water moving over the surface, it would easily move through erosion the topsoil and all the nutrients that are essential for plant life, while the organic material protects it. It helps to reduce erosion by keeping everything in place. So the process of soil formation is a slow process, and it really depends on climatic conditions. Um, whether that's a tropical location with warm temperatures and loads of precipitation, or a dry condition, an arid condition without much precipitation and higher temperatures, all of these things will result in different rates of both chemical and physical weathering and different rates of decomposition. So soil development is highly varied across planet Earth. Nevertheless, overall, it's quite slow. Um, and as you can see, we start off with unweathered bedrock in stage one. So we have exposure of Earth's crust to the atmosphere. Chemically and physically, that breaks down. Over time, not only is it breaking down chemically and physically, but now all of a sudden, plant life starts to take hold. It utilizes this substrate as a platform for growth. Perhaps a bird flew over and defecated on the rock with some seeds, perhaps, and it allowed for the germination of some pretty hardy plants, and then over time these plants grow, accumulate, die, decompose, making organic additions to the soil. And so what we get is this interesting gradation over time where we see organic material close to the surface where there's biologic action, right? A lot of biotic material. And then it becomes more physical in nature the deeper we go as we get closer and closer to the bedrock or crust. Right? We can actually visually see this, right? We can see more consolidated bedrock, weathered rock, and then it gradually becoming more organic with the root penetration and organic material close to the surface. So as this process continues, what develops are distinctive soil horizons. Again, more lasagna. Yeah, so we have these layers, and each layer is sort of unique from each other. They're unique in terms of their chemical composition, their physical properties, particle size, right? Is it clay, sand, or silt? And then, of course, level of organic material. Obviously, more organic matter is closer to the surface, and it becomes more physical the deeper you go. Now, all of these things, these differences in these characteristics become highly noticeable as you dig deeper and deeper into the soil and create what we call a soil profile. What you'll notice is that as we dig deeper, you start seeing dramatic changes in color. And as a result, each layer can be sort of separated from each other based on differences in color, which are indicative of changes in composition, physical properties, particle size, and especially organic matter. Right? Generally speaking, when you get to layers that are much darker than others, it is highly indicative that it is rich in organic material. You only have to think of a banana, for example, that when it decays, it becomes dark and black over time. So these darker colors are usually correlated to an abundance of nutrients. So here we have a typical soil pedon, which is sort of a classic unit that we find in a soil profile as we dig down vertically through the soil. This particular sequence of soil horizons is something that we would see out in the Lam Woods, for example. And what soil scientists do is they actually abbreviate each horizon with a letter, and these letters represent the individual layers that change with their chemical and physical characteristics. So the classic soil profile that we need to get to know for this class starts off with the letter O, which is the first bracket of the soil horizon, A, E, B, C, and R. So let's go through each horizon one at a time and get to know their major characteristics. So we'll start at the surface and work our way down. The O horizon, which stands for, of course, the organic layer. This is the surface. So in a forest ecosystem, for example, a deciduous forest ecosystem, every autumn we would have leaves falling from the trees and accumulating on the forest floor. And in fact, any plants or animals that live on the forest floor that eventually die will then settle to the floor of the forest. Now, this is known as the O horizon, or organic layer. It's considered the leaf litter. This, of course, is a really important nutrient reservoir, as this organic material slowly decays, releasing organic material into inorganic nutrients in the soil itself. So the O horizon is our leaf litter. This organic material is adding critical nutrients to the A horizon that sits directly below it. The A horizon is also known as the topsoil. This is what a farmer is concerned about. This is the plow zone, and this is the layer of soil that we plant our crops. The A horizon is the topsoil. It consists of both mineral matter, so in other words, broken pieces of rocks and sediments, mixed with the organic material that was added by the O horizon that sits on top of it. So it'll be rich in humus, which is the partially decomposed plant and animal material. Since there's a lot of organic material, this topsoil tends to be dark in color because it's rich in nutrients. Now what happens is, after this A horizon here, we end up in what we call the E horizon, because in the A horizon, rain is infiltrating down through the A horizon, and it's dissolving the critical nutrients through a process we call leaching. Now this doesn't become bleached in the A horizon because we constantly get organic additions to it from the O horizon. However, through that infiltration and leaching down below, we then end up with the E horizon, which stands for the zone of eluviation. When I think of E, I like to think of exit, because what's happening is all the nutrients that were in this location are being leached out or dissolved and carried to a lower horizon. This is called the maximum zone of leaching. ZO is zone of. This leaves a bleached mineral horizon in its wake, right? All of the nutrients, or a lot of the nutrients, have been dissolved through the leaching process, leaving it nutrient deprived, giving it a very pale, bleached mineral appearance to it. Everything that exits the E then accumulates in what is called the B. This is the zone of illuviation. So eluviation is where it exits, illuviation is where it enters and accumulates. Everything that was removed from the E horizon above it accumulates in the B horizon below. Certain minerals are highly stable deep within Earth's crust and within the soils. However, with all of this eluviation and leaching, that water moves its way down into the B horizon, creating some chemical reactions with feldspar, for example. Feldspar, when undergone combination and chemical reactions with water, undergoes hydrolysis to form clay. And so consequently, the B horizon is really rich in clay, and you get to what we call a hard pan, or a sticky layer of clay formation in the B horizon. The B horizon sits on what is known as the C horizon, also known as the parent material, or the weathered bedrock. In other words, if the soil formed in place on the bedrock, on the actual crust itself, that parent material would be very similar to the bedrock that it weathered from. What's interesting for where we live is our parent material is not local. It's not residual. In other words, our parent material was transported by our last glaciation and the glaciers that covered much of New York State. 10,000 years ago, there was a mile-thick sheet of ice that advanced from Canada over New York. That glacier was like a giant bulldozer that scoured the Canadian landscape, carrying with it a load of rock and debris. When the glacier melted and retreated, it dumped out that entire debris pile in New York State. That is our parent material. It is the glaciated deposits from over 10,000 years ago on which our soil is formed, which is very different, of course, from the bedrock it sits on. And the bedrock is, of course, our final layer, known as the R horizon, or regolith. And this represents the crust of the Earth. It's the unweathered, hard bedrock. Those are your soil horizons. We're going to be exploring these out in the woods in class next time, and so we look forward to that. Take care, guys. Bye.